Okay, so here we go. So combiner is like a reducer which runs on the same node on which the mapper is running. Okay, so instead of the whole work to be done by the reducer later on, we get some of the work done on every individual node. Okay, so this diagram, if you see, the data from mappers is coming in. Okay, key values are being generated, and for the same key, if there are multiple values coming from multiple places, the combiner combines them. Okay, and then the partitioning happens, and then the data goes to the reducer. Okay, this way the traffic is minimized. Now, one important aspect which I want to discuss again is that only those kind of work can be done using combiner, where you can keep applying the same function again and again in irrespective of the order. It is still is gives the same answer. For example, sum, minimum, and max all are valid combiners, but average or mean is not a valid combiner. Let's take a look at the code, the SG test one, the second project which we have mentioned on the LMS. Here, there is something called care count. So here, if you see the driver, right? If you see the driver, we are mentioning partitioner, setting the partitioner, setting the combiner. It doesn't enforce any kind of ordering. Okay, we basically creating this large object of job, setting all the parameters, and then executing in a single shot. Okay, so there is no ordering per se, that we are not doing partitioning first and combiner. Okay, here in the diagram shows the order in which things are actually happening while execution on Hadoop. First, mapping is happening, then the combining, then partitioning, then this transfer of the data over to the reducer, and then the reducer process starts. Okay, so we do not enforce disorder. Hadoop enforces disorder. Okay, we only hand over all the information to Hadoop job and start the job. All right. So the one thing which I have been discussing and I wanted to demonstrate is that, let's say you have four values: 1, 23, 10, and 15. What is the total of these four values? So the total is 49. And now, no matter in what way you do the addition, the result will be the same. Whether you add all of them in a single shot or in parts, okay, the result will be the same. For example, let's say you want to only sum up these three values, okay, or let's say you want to just sum up first these two. How much is that? Let's say you want to sum up 23 and 1, it's 24. Pretty simple, right? Similarly, if you sum up 24 with the summation of these two, how much is 10 and 15? Anybody? So 10 and 15 is 25. Now when 25 and 24 are added, okay, you get 49. Okay, 49. So here the quality of summation is that no matter in what order you apply the function called summation, the result will always be the same. Okay, no matter how you apply. Let's say instead of doing this way, we first sum up these two. Okay, and the answer is 34. Okay, and then we apply summation of 15 and 34, the answer will still be the same. Okay, so no matter in what order are you doing the summation, you are always getting the same answer. Similarly, let's say we were doing the max. Okay, max of all of these will be 23, no matter from where you start counting. So for example, the max of 1 and 23 is 23. Max of 23 and 10 is 23, and max of 23 and 15 is 23. No matter in what way you apply max, min or summation function, you always get the answer, right? Because this combiner function is not applied on all values at a single go. It is applied as and when the sorting is happening, and whenever the sorting is happening, so the two values are being compared and sorted. Okay, if you have gone through the sorting algorithms, so whenever the existing process of sorting is happening, your function of combiner is being called. Okay, so that while sorting itself, the grouping happens and the merging happening, so there is no extra burden or extra pass required for executing combiner. So combiner is executed while the sorting is happening. So in the combiner function, you can do these kind of magic so that the data get reduced drastically. The work is solved at the combiner level itself. Okay. Now, a bigger question. So why I'm emphasizing on a combiner, this kind of a property of combiner, because combiner is used in many other distributed paradigms, such as the standard Spark reducer. Okay, so when we discuss about Spark, you will know that. Now, let's say your function. Let's say this is the code in your combiner, and what does this code do? So this function which we have written here, what it does is it returns the square root of sum of squares of all the values that are passed to it. Okay, the way we were doing summations only, here this particular combiner is doing the square root of the summation of all the squares of all the values. Now question is this function, this property which we have talked on this page, it's called commutative and associative. Is this function valid combiner? Because commutative and associative, computing commutative and associative, we should have a clear picture. Okay, all right, let me try to show you this. Okay, let's say we had how many values? Let's say we had x, y, z, and u. Okay, so what is the function we have? We have this function, you see, we have this function. Now, what if we apply this function on all the values in a single shot? We will get x square plus y square plus z square plus u square and the square root of it. Okay. Now the same function, if it is applied on only two values, okay, we get, what do we get? Let's say we get w, and this w is square root of x square, okay, plus y square. Okay. Similarly, when we do the same thing here, okay, let's say we get v, which is square root of z square plus u square. Okay, now when these two values get combined, okay, what would happen is it would be the answer would be v square square root of v square plus w square. Okay, and which is square root of square root, this is square root, don't confuse it with the square, this is square root, similarly everywhere it's square root. Okay, and the square root of and what is v square? V square is equal to z square plus u square, z square plus u square plus, now what is w square? W square, if you do the square on both the sides, w square will be equal to x square plus y square. Okay, so you can see clearly that when the values are getting combined, this function is actually a valid commutatively and associatively. Okay, So no matter how you apply this function on these values, the answer will always be square root of x square plus y square plus z square plus u square. Alright, now let's start our discussion with of job chaining. Okay, now what is job chaining? So whenever you need to work on a larger problem, you might have to break down your big work into map reduces. And quite often, your work would involve multiple MapReduce phases. I remember my work on recommendation engine involved around 5-6 phases of MapReduce on my side while I was cleaning the data, comparing the normalization and all that. So when you have that kind of requirement in the and you'll end up breaking down the problem into multiple phases of map reduces, and because it's not theoretically possible to have all the map reduce work to be done in a single map reduce phase, because in one part you might require grouping on one field, in another part you might require grouping on another field, right? So so effectively you will have multiple map reduce job to be executed sequentially. Okay, so the output of first map reduce job becoming the output input of the second job, and the job chaining, the most simple way is create the two job objects, job 1 and job 2, and wait for job one's completion and start the job 2. This is the simplest, most way of executing, doing the job chaining. All right. The next way of job chaining is using the Unix command. I'm not sure if you are aware, but in Unix, what you can do is command 1 ampersand command 2. Okay, this from here to here is the first command, and this here to here is the second command. So you can execute first command and wait till the first command runs successfully and then execute second part. So Unix provide you this functionality of ampersand, which makes it possible to run to any two commands in sequence. Execute, this basically means execute second command only if the first command is successful. And what we are doing here is executing first driver and then ampersand executing the second driver, and that's it. Okay, here there'll be a jar file as well. I forgot to mention the jar file here. So Hadoop jar, my jar file 1 and driver 1, similarly Hadoop jar, same jar file again, and driver 2. Okay, so it could be same jar file or different jar file, it could be anything. So any two command using Unix can be sequentially executed this way. Now the third method is using OZ, that we'll discuss later, and fourth method is using dependencies. Okay, we could, the Hadoop provides a way of creating dependencies. All right, so I like the first method and I like the second method using Unix, and in a very complex projects the Uzi is the solution, but dependencies is also a way of executing things. Okay, but this is, so there is no single way and there is no I mean way of justifying one approach against another. All right, so you could take a look, you could download this project or just download some this piece of code and add it to you, just a second. Okay, so you could download this piece of code and try it out, and you will find out that it's actually quite straightforward. I'll show you this. So you can see that the chain driver is quite straightforward here. So here you first of all you proceed with the usual format. Okay, creating first job object and creating the second job object. Okay, and then you create a wrapper called control job on job 1, and then you create another control job on job 2. Okay, you create another control job on job 2. Okay, and then you create something called a job control. Okay, and you add these two jobs, job 1 and job 2, into job control, and you also define a dependency between the control jobs. Okay, so these are the wrappers provided by Hadoop library to make it possible to have a complex structure. So this way you can create the chain job. There's nothing magical about it, but it helps us in putting the many level of dependencies. Sometimes you have 10 map reduce phases where first depends on second, depends on third, and so on. Those kind of problems can be well solved using the control jobs. Okay, so you do not have to decide which one to start first. Okay, you leave that to the driver to execute. You just focus on creating the dependencies. Rest is taken care by the okay. So that is job chaining. Sometimes people ask about pipes. Okay, pipes is the way we were trying to execute the MapReduce streaming so that we could use any kind of code as map and any kind of code as reducer. Here, in case of pipes, so the way we said Hadoop, jar, and something, similarly, we could say Hadoop pipes. Okay, Hadoop pipes and provide the input path, output path, and the program, and it'll do the execution. So the pipes command has been explicitly created for those who are looking for performance. They use pipes, and specifically people who are working on C and C++ kind of environment. Okay, so for them, pipes is the answer. So they can use Hadoop pipes if you are using C, C++, and your performance is the first concern. All right. Then another idea called speculative execution. What is speculative execution? It's like a overreactive manager. So those people who have there are some teams, there are some companies where you will find these overreactive managers. Their sole objective is to get the work done fast, no matter what it takes. In those cases, what they do is they'll put, let's say, three people on the work. They will divide the work into these three people, and whosoever finishes faster, they give the work of the one of somebody else who is still busy to the first one. So the work is being done twice, and whosoever finishes first, their work will be considered, while the one who hasn't finished yet will be ignored. So let's take a look at the actual example here. So let's say there are four task trackers, task tracker 1, 2, 3, 4. Okay, so what Yarn will do is we tell that here are the four tasks, and we are enabling speculative execution. So task tracker 1, 2, 3, okay, and 4 are given the work. Task tracker 1 and 2 quickly finished, and 3 also finished very quickly. Now, the work which was still running at task tracker 4 is given to task tracker 3 as well. Okay, just out of it could have been given to 1, 2, or 3. In this example, it has been given to only 3. Okay, now let 3 run for some time, and whosoever wins, whether task tracker 3 finishes the task 4 or whether task tracker 4 finishes task 4, whosoever finishes first, their output will be regarded. Otherwise, whosoever loses here, task tracker 3 or 4, their output will not wait for that and will just kill the process. So at the point, at the time 0, all 4 of them started. After some time, all 3, 1 and 2 and 3, finished, while task tracker 4 is still running. Now same work which was assigned here is also assigned to task tracker 3. Okay, so basically from here, same work got assigned to 3. So now we are letting both of them do the work. Okay, and at this point, task tracker 3 wins, and task tracker 4 is still working on it. Therefore, here at this point, the task tracker 4 is killed, and the results are stored. There could be another thing, that task tracker 3 is taking long time. Okay, long time to finish, and in that case, in case task tracker 4 finishes first, then that answer will be regarded. Okay, so because right now, uh, Hadoop does not know whether it's a problem with the data. Okay, the work which is given to task tracker 4 may be really really huge, or maybe task tracker 4 is really really slow. Okay, in order to if the objective is to get things really fast, then speculative execution is important. In case your resources are important, okay, and you don't care about fast execution, then you don't go with speculative execution. What if both are not finishing? Let's say task tracker 4 is also running and task tracker 3 is also running, and they're taking time. So Hadoop will wait for both of them to finish. It won't execute more than 2 copies for speculative execution. Okay, not more than 2 copies. I think that is configurable probably. Okay, all right. So that was speculative execution. So what are the various writables available to us? So yesterday, while we went through the Java code, so here what we talked about the custom writable. So objects that are serialized need to extend writable. As I was telling you, that the key and the value need to be stored somewhere, so that they need to be transferred to some other machine for reduce phase from the map phase, right? Similarly, there are many times the key and values are serialized, deserialized. Serialized and deserialized means saving to the disk and reading from the disk. Okay, so basically anything that needs to be written to the disk or to the wire as in when I transfer data from me to you, as I'm speaking right now, the data is getting pushed to the wire, right? And that's where the serialization comes into play. Okay, all right. So objects are serialized, need to extend an interface called writable. Okay, so text, int writable, long writable, float writable, boolean writable, these are the predefined objects provided by Hadoop to you. Okay, you can see all kinds of writables here. Okay, not this one, not this one. Right, writable. Okay, for example, you have sort writable, and it's extending. Right. You can see there are so many writables available. Okay, there's so many writables available, different kind of writables. So anything that gets transferred over the wire in Hadoop actually is a writable. Okay, and if you want to create your own writable, all you need to do is define an interface called writable, and it should be able to read fields from the input binary data and convert data into the binary output using while writing. So your object need to know how to read data and write data. That's it. So you can see that it's a little involved process to converting binary data into fields, right? So this writable converts the binary data into the, so every one of them, text, int writable, long writable, float writable, knows how to convert binary data into a value. Okay, so this is custom writable. All right. Now there is another very important idea which we all should know, is data locality optimization. Okay, and what exactly is data locality optimization? Okay, so Let's say you have data center and these data center have racks. And what is a rack? Rack is like a big almirah in which you stack computers. You put computers one on top of, it has sections for putting computers. You can create custom rack or you can buy pre-built racks. Okay. And in the rack, whatever computers you put, those all computers form a local area network. Okay, so every rack is a network itself. So the data transfer between two computers on the same rack is faster than the data transfer between the computers which are on two different racks. Okay, so the data transfer between a computer here and here is faster than here and here. Okay, all right. Now, data center is composed of many such racks, and the task trackers as well as job trackers and as well as data nodes are spread across the cluster. Okay, so let's say you have HDFS block here. If you run your map task here, this is the best case scenario, meaning the computer on which the HDFS block was available, okay, has got is running map task. And sometimes that node might be busy. In those cases, the task tracker might be executing. The map task might be working on the same rack but different node. Okay. But in the worst case scenario, if task tracker is running on some other node and the HDFS block is on some other node, it is going to be the worst case scenario. All right, because the data transfer would happen because map task needs to read the data. Here data transfer is happening over a same local area network, while there is no data transfer happening here. Only the time taken to read data is how much time it takes to read data from the disk. Okay, so this is called data locality optimization. So what is data locality optimization? Hadoop preferring this over this over this. Hadoop prefers A kind of a situation over B and B kind of situation over C. Alright? Now, quick question to all of you is, can reducer take the benefit of data locality optimization? So after the map task finish, all of this data has to be brought to a single or multiple nodes, right? It has to be transferred because reducer might be, at most what you can do is if you are running reducer on the same node as map node, okay, as one of the map tasks, at most only that particular node's data you don't need to transfer somewhere, but other nodes data has to be transferred, right? Therefore, in case of reducer, you can't really take the benefit of data locality in case of reducer, right? There is a very common question where if you have to store a file with replication factor of 3, on which all nodes will Hadoop store the replicas of a particular block? Let's say you have to store a file in HDFS. So what are the nodes it will select? If you remember, you'll have to keep, say, 3 by default replication factor is 3. So there will be 3 copies of the same data. So where will these 3 nodes be? On the same rack, on the same machine, or different racks, or how would it be? So the first one will be on the local node. Second one, local node as in if you are standing on H1 and H1 like you are in the console, web console, the one which we have created, you are on one of the computers and you are transferring data from local machine on that machine to HDFS, right? So in that case, you are on the same machine as this one. Although even if you are on a remote machine, you can install Hadoop client, okay, and specify that hey, I'm trying to upload to that server. In that case, you'll have to provide the login password. And So the first copy will be on the local node, as in if you the same node on which you are logged in, and second one on the same rack, and the third one will be off the rack. Okay, meaning on some other rack. That other rack could be in the same data center or other data center. You could take a look at this strategy which I have mentioned here. It's called HDFS, replica placement policy. This particular question comes under replica placement policy. Okay, you can take a look at there. All right. So the way it computes, how does it compute which nodes are closer to each other and which nodes are farther from each other? It uses something called topology, and topology is defined. You have to define the topology. Now, how do you define the topology? The way to define the topology is converting every computer into a file path. Okay, converting every computer's name into a hierarchy. Okay, for example, here node 1 means s1 slash r1 slash n1. So you have to convert, you have to write a small script which converts an IP address into a path like this. Okay, because the folder structure, the file system, is a very good example of a tree, right? Therefore you have to convert an IP address into a tree, and based on this tree Hadoop will figure out the distance. Okay, so what you do is you take a node and give a name to it in the form of a tree, s1 slash n1 slash r1 slash n1, s1 slash r1 slash n2, and so on. Okay, this is network topology which you define. And how do you define? You basically write a small script which given an IP address will return the path. Okay, given the IP address of the node, it will return this path, and based on this Hadoop can very comfortably compute the distance. Okay, so this is called rack awareness. So it understands the network as a tree. It is similar to the path as slash a slash b slash c. There is a configuration in core Hadoop which is called DNS to switch mapping, provides a translation from machine name to network location. The config script location is here. Okay, this is the key in which you can write your configuration script, and this configuration script could be any program. Okay, so all it has to do is convert IP address to a name. Okay, and how does it compute? It sums up the distance from common ancestor. So who is the common ancestor of n1 and n2? It is r1, right? And how much is the distance of n1 and r1? 1. And n2 and r1 is 1. So 1 plus 1 is the distance between node 1 and node 2. So node 1 and node 2 are two distance away from each other. Okay, so the way you do is you keep on climbing up till you meet the lowest lowest common parent. Okay, let's say for n4 and n1 you'll keep on moving up from both the sides, and this common parent is switch 1. So the total distance will be 1 plus 1 plus 1 plus 1, which is total distance between n1 and n4 is 4. All right, that is the distance that is computed. Okay, so the bandwidth between n1 and n1 is maximum, while n1 and n4 is minimum because the distance is bigger. Alright, so the distance between node 1 and node 1 is how much? 0. Now the distance between n1 and n2, just based on this path, you see the path? Path says d1 is the parent of r1 is the parent of n1, and d1 is the parent of r1 and n2, which means the common parent of n1 and n2 is r1, and so the distance between the n1 and n2 is n1 and n2. So the parent is r1, so summation of the distance between n1 and r1 plus and r1 and n2, which is 1 plus 1, and the distance between n1 and n3. Who is the common parent between n1 and n3? So 4. Brilliant. Now similarly here, so distance, if there are two data centers you have, then you have this kind of. So visually, this is how it's presented. There are two data center D1 and D2. Both have racks and there are distances. All right, that's pretty much about the MapReduce.